put the Barra in embarrassing.
Oh, I actually like that. Yes.
Alright, so here's how we're going to do a modified Atwoods machine. And it's very similar to when you have two masses slung over a pulley and you're going to treat the entire thing as a system. In this situation, we have a 10 kilogram block hanging over a pulley that's attached to the building. So you can ignore the pulley, but it still acts like a way to create the two-dimensional object just stretched out into one dimension, or reversed. We have a 5 kilogram car attached to the other side, and it is a smooth surface, so we're going to again pretend that friction does not exist in this situation. Whenever you're looking at a dynamics problem or a forces problem, the first thing you need to do is label all forces acting on both objects. So for the box hanging on the right side, we have its weight, or the force of gravity, hanging down. And I'm going to call this object B and object A because they're both going to have a weight. And I want a way to differentiate them in my mind. So FGB, and we have tension up. For this car, we have the weight acting down, the normal force acting up, and the tension pointed to the right. If there was friction, there would be a frictional force going backwards. I'm going to do this problem frictionless, and in the second half of the video, and I'll try to put a link in the time, or a timestamp link down in this corner of the video, you can jump ahead to that if you want to jump right into the problem with friction. But for now, it's a frictionless surface, and we're going to treat it exactly like we did when we had two objects slung over a pulley. And just like before, you can always take them and stretch them out into a straight line to help you conceptualize it. And if that's the case, we have a block, and if we stretch it out, the force of gravity is pointed to the right, and tension's pointed to the left, attached by a string to our car. So it's the exact same thing. And we really only care about forces that are along this plane of movement. It's not going to get pushed to the left or to the right, and this object's not going to get pushed up or down. It's all along this imaginary curved axis that we've created, or the axis of movement. So now let's actually look at the forces that are affecting the acceleration. And remember, acceleration is caused by unbalanced forces along our axis of movement. In this case, our axis of movement is affected by FGB, FT, and FT. And remember, there are two ways to approach this. We can treat this entire mass as a one-mass system, and then you can ignore internal forces, or you can add FT and subtract FT. It's the same thing, and you're going to still find that the only unbalanced force is the weight of object B. We can ignore normal force and the weight of object A because they are perpendicular to the movement. And remember, vertical forces have nothing to do with horizontal forces. So these forces don't have anything to do with whether it's going to move left or right. And just like before with the pulley, we're going to treat it as a system. So the net force equation is where we're going from here. The net force of the system equals the mass of the system times the acceleration. The only unbalanced force we have is FGB. And I'm going to treat any force pulling it to the right as positive and to the left as negative. So any force going this way would be positive, and any force trying to push it this way would be negative. It's the same thing, I just stretched out so it would make more sense in my mind. But you can do it either way. And that's equal to the mass of the system, which would be the entire mass of everything connected by the string. So that would be the 10 kilogram block plus the 5 kilogram block. So the mass of the system is 10 kilograms plus 5 kilograms times acceleration. And remember, the weight of object B is equal to mass times gravity. So that's equal to the mass of this object, 10, times gravity, which is 10, and you're going to get 100 newtons. And we can plug that in for FGB. 100 newtons equals 15 kilograms times acceleration. To solve for A, we just divide both sides by 15 kilograms. And when you do that, you're going to get an acceleration equal to Thank you so much. 6.67 meters per second squared. Now, if we wanted, we could plug this in to solve for the tension, just like we did before. So to do that, you need any object that has the tension acting on it. In this case, object A only has one force acting on it, tension, or at least one force in the direction of acceleration. So the net force of A equals the mass of A times its acceleration. So the net force of A is tension. And it's going to be positive because it's to the right, and I chose any force to the right as being positive. So positive Ft equals 5 kilograms times our acceleration of 6.67 meters per second squared. And when I multiply those out, I'm going to get 33.3 newtons. Now, you could have plugged this acceleration into a net force equation for the 10 kilogram mass and you would have gotten the exact same result. And if you want to, I encourage you to go ahead and try and see how you do. So now, done with this, but we're going to redo the exact same problem, except we're going to introduce a coefficient of friction equal to 0.1. It's the exact same problem and the exact same setup. We're just going to get a slightly different result. So we have our car of 5 kilograms over a pulley and attached to a 10 kilogram mass. And again, our first step whenever doing forces problems is we need to label all forces acting on either object. So we have the weight of object B, and we can go ahead and plug in our mass times gravity, 10 times 10, which is going to be 100 newtons. And for this 5 kilogram object, we have the force of gravity, FGA, which equals 50 newtons. We also have normal force, tension, and friction. For this object, the one force I missed was tension. And you can treat this the exact same as we treated this situation before. You can straighten it out and look at horizontal forces. When we do that, we have our car attached by a string to a 10 kilogram box. But remember, when you stretch this out, FGB is going to be pointing this way, and FT is going to be pointing to the left. And for this, FT is going to be pointing to the right, and the force of friction is going to be to the left. When we treat this as a system, we only care about outside forces, which means we can ignore both tensions. So now, our unbalanced force for the system is FGB minus the force of friction, because anything to the right should be positive and anything to the left should be negative. You could switch those, but you need to be very, very, very careful to be consistent about what's positive and what's negative. So now that we have that, we're going to do our net force equation for the system. Net force of the system equals mass of the system times acceleration. Net force of the system would be FGB minus the force of friction. And that's equal to the mass of the system, which again is going to be the mass of both objects added together. 10 plus 5 is going to give us 15 kilograms times the acceleration. We know FGB is 100 newtons, so 100 minus FF equals 15A. Except now we have two unknowns. Acceleration is unknown and friction is unknown. And this is where you come back to your very first day that we discussed forces and how we calculate the force of friction. Super straightforward. Your equation to solve for force of friction is coefficient of friction times the normal force. Except now we don't know the normal force acting on the car. But we know that if you look at these vertical forces acting on this car, they are going to have to completely balance each other out because the acceleration is along the horizontal axis and not this vertical axis. So your weight has to be perfectly balanced by the normal force, and your normal force is 50 newtons. So then we plug that into our equation. 0.1 was our coefficient of friction times the normal force, which is 50 newtons, is going to be equal to your force of friction. So the force of friction is going to be 45 newtons. Once you have the force of friction, 5 newtons. 5 newtons. 5 newtons. Thank you, buddy. I'm really glad you're here. And then we're going to plug that into this equation. 100 newtons minus 5 newtons equals 15 times A. So 95 equals 15A. And then when we solve for A, you're going to get a number.
6.3 repeating.
6.33 meters per second squared. And that should make sense because we have the exact same setup, except now we have more of a frictional resistance. More friction means it's not going to accelerate as quickly.